Okay, good morning once again, one and all. So, we have previously made a video that is a part of part 1 for the design of knuckle joint. So, in that particular video, that is a part 1 of knuckle joint, we have understand the different types of joint, then the applications of knuckle joint, what is exactly knuckle joint. Then I have explained you the knuckle joint components. Basically, it consists of three: fork, rod, and the pin. Then the very important free body diagram, that is the forces acting on the fork end, iron and the pin. Then we have also understand the schematic diagram, and then by we have used the diagram from PAG 7.139. Then considered a different notations like diameter of rod, D1, D2, D3, T, T1, T2. Then we started with the exact design, actual design, that is a designing a knuckle joint to transmit axial tensile load of 50 kN. So in part 1 we have selected a material C35 based on the yield strength, that is a failure criteria is yield strength. And we have selected factor of safety 2. Then as I said in the previous video, that the loading conditions in the knuckle joints is nothing but the tensile, compressive, that is a crushing, as well as the shear stress. So we have calculated all the design, that is a permissible allowable stresses sigma t, sigma c. So we have to remember this for further calculation. So allowable tensile stress 155, allowable crushing stress 232, and allowable shear stress tau will be 77.50. So all the further stresses acting at the eye end as well as the fork end should be under this allowable stresses for design to be a safe. Then we started with the part 4, that is the design of rods D, D1 and D2. So what is D? Diameter of rod, that is rod A as well as the rod B, that is a rod connected to the fork end as well as the eye end. So finally we got D is equal to 22.0 mm. Then using empirical relations we calculated capital D1 capital D2. These empirical relations are mentioned already in the diagram available at page 7.139. I am repeating again and again, page 7.139. So D1 and D2, enlarged diameter of fork and enlarged diameter of eye. Then we decided the thickness of eye end and the fork end, that is T and T1. So remember this, T is 30 mm and T is 18 mm. So T is nothing but the thickness of the eye end, T1 is nothing but the thickness of the fork end. Just remember that there is one eye and there are two forks. Okay, so if I go back, because that will be helpful for you to understand. If I go back, you can see this. Okay, two forks having a thickness T1 and one eye having a thickness T. Okay, so the important part is that this is the outer end, that is a diameter D2, that is the outer diameter of the fork end, as well as the outer diameter of the D2, that is outer diameter of the eye end, will be same, that D2 is equal to D2. So it's one and the same. Okay, as well as this inner diameter. What is this inner diameter? This inner diameter is nothing but a diameter of this pin, that is D1. Okay, so basically if I draw a circle over here like this why I am explaining you will understand later. So this is nothing but the outer diameter D, D2, and what will be the inner diameter? Inner diameter, I am talking this for both fork as well as eye. Remember this, inner diameter will be D1. Okay, and if you talk about this thickness is T for the eye end, and for this it is T1. Okay, so if I want to calculate the area resisting the tensile as well the shear failure, which we'll understand later on. So normally we'll get this area will be equal to d2 minus d1. If it is a I, it will be d2 minus d1 into t. If it is a fork, it will be d2 minus d1 into t1. So to calculate that area for some tensile as well as shear failure for the I as well as the fork, this d2 minus d1 is common, right? But t1 and here t will change because thickness is changing. This you remember for further analysis. I hope it is clear to all of you. Then we calculated, yeah. So then today we will understand the step 4, that is decide the dimensions of the pin. Now what is d1? D1 is nothing but the diameter of the pin, and basically it is not D2, it is basically a D3. What is D3? D3 is the diameter of pin head. This is the diameter, right? This is nothing but a D3, and this is D1 already we have understand, right? So now, as I said already in the last video, that let me erase this, let me write this 3, that this pin is subjected to the both the failures, bending as well as when the pin is tight inside the eye and the fork, it will be subjected to the shear. So as I explained you in the earlier video, that it will be a under a double shear. So this is the first area resisting the shear failure. This will be the second area resisting the shear failure. Means what, this pin will get cut in or sheared into the three pieces, right? Okay, so you can see it is shearing at this area and it is shearing at this area. So this exactly the portion where it is sheared is nothing but the T, the portion which is lying inside this eye having a thickness T, and this two portion is T1 and T1 is nothing but the exactly the portion which of a pin which is lying inside the eye, sorry, inside the fork. Is it clear? So now basically the pin may get sheared off into the three pieces as I explained. So both the areas are taken as a resisting areas. So this area also and this area also, because I'm explaining here. This is a resisting area. This is the resisting area. Okay. Is it clear or not? Yeah. So now let's calculate this first of all. So as far as the exam point of view is concerned, this figure is sufficient to understand. Okay. So how do we calculate the shear failure? So we know that the shear failure of the pin is given by tau is equal to P upon area. Now what is the area resisting the shear failure? What is the area resisting the shear failure? What will the area resisting the shear failure? Obviously this area, we move back, this area is nothing but a circular cross-sectional area having a diameter d1, so pi by 4 into d1 square, so not so big deal. So area resisting the shear failure. Now this, what is this now? This is nothing but the tau, which is called the, already I have calculated. So now you might have understand why I have calculated this allowable shear stress. So what was the allowable shear stress? We can also write it as the T allowable. Okay, but you remember that it is allowable shear stress means what, the shear stress inside the pin should not exceed this allowable. In such a case you have to select this D1. So ultimately I am calculating the dimensions from the stress analysis, try to understand, and in some cases I am considering it as a, what can I consider as a empirical relation. So from this, P is nothing but 15 to 10 is to the kilonewton area. Now 2, why I have taken a 2? Because it's a double shear, means there are two areas resisting the tension, so take it as a double shear. So 2 into pi by 4 d1 square. So from this I am getting 22. As I said that you can also go for 21. So normally I try to take a even figure. It will be helpful for the calculations, not any theoretical logic behind it. So d1 is equal to 22 mm. So now basically, is this, can we final this 22 mm? No. Why? Because when the pin is tight, when since this is a sliding joint, and when the pin is loose, when the pin is loosed, what happens? It will be subjected to a bending failure. So maybe that if you are considering T1 is equal to 20 mm, this pin will not get fell under the shear, but it may not be sufficient for the bending failure. So this pin may get failed due to the bending. So what we have to do, we have to calculate again D1. Let us say you have calculated D1 by using a bending failure criteria, and let us say it is a 25 mm. So obviously you have to select D1 which is greater, so the D1 will be selected as a 25. So guys, try to understand that you have to do both the analysis, bending as well as the shear analysis, and the greater of the two you have to select, because if you are selecting a greater, obviously it will not fail for both shear as well as the bending. Is it clear? So now how do you do the bending analysis? That is the point. Now you can see this is a pin. I have considered it, I have placed it horizontally. Okay, this is a pin. You can see that the middle portion is subjected to some stresses. Okay, and this portion is subject to stresses. Now basically what is this portion? First of all, this middle portion is nothing but a portion which is lying inside a thickness T, that is a I, and this portion, these two portions is nothing but a portion of a pin which is having a thickness T1, means lying in the two, sorry, not I, two forks, right? So obviously it is very basic to understand that this middle, these two, sorry, this I will just clear it out. Okay, so this middle it is very basic to understand that this middle portion, okay, here the load acting on the pin, I will write here the load acting on the pin, load acting on the pin is have uniformly distributed load in I, right? The load acting on the pin is uniformly distributed in the eye, so it is assumed that load acting on the pin is uniformly distributed in the eye, because this portion is the portion of the pin which is lying inside the eye. Is it clear? So we have to do the strength of material analysis, bending moment. So for this middle portion, this portion will do the uniformly distributed analysis, right? Now I'll just move on to the next part. Now this portion which is lying, portion of a pin which is lying inside the fork, so it is assumed that it is uniformly varying, so the load is uniformly varying load in two parts of the fork, two parts of the fork. So is it clear? So let me explain again. So in the eye end it is assumed as uniformly distributed, and in the two parts of the fork it is assumed as a uniformly varying load. Okay, so now let's do the analysis for this. So now first of all consider this middle portion, sorry, I will not consider the middle portion. First of all I will consider this triangular portion. Now we know that for triangular analysis, we have already know this, just I will for a basic, let us say this arrow indicates a stress distribution. You can see the stress is starting from 0 and it is going to maximum over here, so stress distribution. Okay, so now let us say this load is acting somewhere here, load is acting somewhere. What is the load acting? This load is nothing but a p by 2. Okay, so let us say this load is nothing but a p by 2 which is acting somewhere here. Okay, so let us say this distance is x from here to here, and this distance is y. So we know that this x, and obviously what will be this total length? This total length is t1. Why? Because this portion is inside the eye end and the thickness of the eye end is t, thickness of the eye end is t1, right? Sorry, I'm so very sorry, this we are considering this one na? So the thickness of this is nothing but a t1 because this portion is in the fork, right? We are doing the uniformly varying analysis, so t1, this distance is t1. So what will be the x from this side if you consider? Okay, this x will be equal to 1/3 of t1, right? This s will be, x will be equal to 1/3 of t1, and from if you this side if you consider, okay, this distance y will be nothing but a 2/3 of t1, right? This is a simple analysis what we are doing. Okay, so similarly now you can take here, understand here, for the triangular distribution of a load between the pin and a fork. Now these two are obviously common, so we'll do it once. Okay, so for the triangular distribution of load between the pin and the fork, this distance x, now you said I have considered this distance x. Now this is the actual diagram and this is the analytical diagram. Okay, now assume that this P2 is acting in here and the half in this part of the fork, and P2 is P by 2 is acting in this part of the fork. How this P by 2 came, we have already understand in the free body diagram. Okay, so let us say this distance is x, this distance is x. X means what? Distance from this point, that is this maximum point of this triangular load, and this distance between the point A and B. This point B is nothing, the point where load is acting. A is nothing but the point where this maximum triangular load is acting or considered. Okay, So how will you calculate this distance x? As I explained, x will be equal to 1/3 of t1, because this total distance is t1. Obviously now from this side you are considering, so from this side if you are considering, it's 2/3. From this side it's 1/3. I am interested in from this side, so x is equal to 1/3 of t1. Is it correct? X is equal to 1/3 of t1. Now if x is equal to 1/3 of t1, that is t1 upon 3. Now let us consider this z. Now what about this z? This z is nothing but the, now basically what has been done, try to understand that this is a triangular load, sorry, uniformly distributed load. Okay, which portion? I portion, having a thickness, means this length will be t, right? Now and obviously what is this force? P1. Now what they have done, they have, what we have done, we have divided this force P into the two parts from the center. Imagine this P by 2 is acting at the center of T by 2, and let us say this is T by 2. So P by 2 is again acting at the center, right? So maybe this is the center of T by 2. So what, tell me, what will be this distance? This distance will be obviously T by 4. This distance will be obviously T by 4, and this distance will be obviously T by 4, and this T by 4 distance is nothing but a Z. Means what? This P by 2, which is acting from this center line, let me call this as a XX, this from the center line XX, this P by 2, obviously this P is acting at half, so P by 2 will be acting at half of T by 2, so P by 2 will be acting at T by 4, and this is nothing but the Z. So guys, what will be this Z? This Z will be 1 T by 4, or you can say half of T by 2, half of T by 2, or you can also take it as a 1 by 140. Okay, for simplicity I have divided this P into the P by 2 because here also I have P by 2 and P by 2. Okay, is it clear? So I have divided this uniformly distributed load, this total length T, I have divided into the half. So this P is acting at the T by 2, so I have considered P by 2 and P by 2, which are acting at T by 4. Is it clear? Okay, so what will be this Z? Z will be T by 4. So in this way I got this Z is equal to T by 4 and X is equal to T1 by 3. Is it clear? Okay, now next, now we have to calculate the first of all bending moment. Now we know that bending moment is maximum at the center. In such case, where the half part of the, in two part the load is uniformly varying, and in the middle portion the load is uniformly distributed, so bending moment will be at the center. You can see this line, this is a center point. Okay, so now how do we calculate this? How do we calculate this bending moment? Okay, so I will explain you. The bending moment MB at the center will be equal to, so you can consider any half part. Okay, you can consider this half part, or you can consider this half part, okay, for analysis to calculate the maximum bending moment at the center. So how I will calculate MB is equal to, so first of all take this distance, take this P by 2, this P by 2 which is acting upward, right? This P by 2 which is acting upward, multiply by distance from the center. So let us say P by 2 is acting here, so I want this distance between the point A and the point B. This is distance between the center. I will write here distance between the centers, from the center, distance from the center. So this will become P by 2 which is acting upward into, because you have to calculate the moment, na, force into distance. So P by 2 acting upward, what will be this distance between the A and B? Yeah, what will be this distance A and B? This distance will be, this distance is nothing but the half of T, means T by 2 plus, what is this distance? Distance between the, let us say, A and O. This distance A and O is nothing but this X. Okay, so it will be X. Is it clear? I hope you have understand this. Okay, so similarly I have got bending moment P, which is P by 2 which is acting upward into T by 2 plus X. Okay, now if I am considering this movement upward positive, means what, it will be clockwise, and downward, sorry, upward, that is and yeah, anti-clockwise about the center and downward clockwise about the center. Okay, so uh, upward I have got, then p by 2. Okay, now this p by 2, now this p by 2, where it is acting, this p by 2 is acting at this point A, and this is point O. What is the distance between the O and A? Is center. So minus p by 2 downward, so I am taking it minus downward. Just remember, forget about the clockwise and anti-clockwise. P by 2 upwards positive, p by 2 downwards negative. So p by 2 into distance is nothing but the z. Is it clear? I am repeating again. This p by 2 is acting here, so this distance A, and this, so I want a distance OA. So this distance is nothing but this t by 2 plus obviously this x, because this distance is O and S. This distance is nothing but the x, and this distance is very simple to calculate. This distance is nothing but the z. Okay, so in this way I will also help you to if you are not able to understand this analysis, it is very easy, but you can remember the direct formula. Okay, so now t by 2 plus x, what is x? T1 by 3. What is z? T1 by 4. Put everything here, we'll just do the calculations. So I am getting maximum bending moment as p by 2 t by 4 plus t1 by 3. Is it clear? So in this way the maximum bending moment at the center is calculated by p by 2 into t by 4 plus t1 by 3. Okay, so this is the first step what we have understand, right? Now we'll move on to the next. Now I, what is I? Now see, this pin is having a circular cross section area. So what will the I? Mass moment of inertia for circular cross section area pi by 64 into d1 raised to 4, very possible. Now what is this y? Y is nothing but this is called as a neutral axis. Again I am requesting, watch all the videos of this basic stress analysis, basic design stresses which I have explained. So there I have already explained that this y is nothing but the distance from a neutral axis to the distance. This is the extreme fiber. This is the extreme fiber. So distance from neutral axis to the extreme fiber, right? Distance from the neutral axis to the extreme fiber is nothing but a y, which will obviously equal to d1 upon 2. Okay, now again I have also explained what is the basic formula for bending moment. It is also again mentioned on PhD 7.1. again you have to watch that videos also. So sigma b is equal to mby upon I. So put m you have already calculated, y we know, I we know, and finally I am getting a basic final formula. Sigma b is equal to 32 upon, now this unfortunately this formula is I didn't find anywhere in the PhD. So if you are not able to do this whole analysis what I have explained you, so you can just draw this figure, or even if you are not able to draw the figure, maybe some marks will reduce, but you can remember this direct formula. Sigma b is equal to bending moment for this particular pin, but it is very useful if you remember this analysis. It's a basic strength of material analysis. So 32 upon pi d1 cube into p by 2 plus t by 4 plus t1 by 3. Okay, so from this we are getting a d1. So we know what is p, we have already calculated t and t1 from the empirical relation. Sigma b means what? Yes, now we'll come to the point. Now sigma b, now obviously again I will request you to watch that videos. I have explained you that whenever you are considering a allowable stress, that is a bending stress. Okay, because in bending stress we have, bending stress means what? It is a combination of both sigma t and sigma c. I have thoroughly explained you this in the video. Okay, so here sigma b, you consider it as a sigma b is equal to sigma t is equal to 155. Okay, you can watch that videos to understand this. Okay, so in bending we considered sigma b, that is the allowable stress, is equal to the sigma t, that is a 155. So from this you are getting d is equal to 28.30. Now you understand that from shear analysis I am getting 22 mm. So if I would have selected 22 mm, this pin would have failed under the bending. So now basically I will select diameter of the pin as 30 mm. So obviously it will not fail for bending as well as shear. This is how we have to do the now empirical relations. What are the empirical relations? Now see this pin head. What is D3? D3 is nothing but a pin head. Okay, this diameter of this pin head. Okay, so basically, as I said, that this pin head is not subjected to any stress. Its diameter is simply decided on the basis of proportionality, that is using a ink. So it is taken as 50% more than that of pin diameter. So what you will take, d3 is equal to 1.5 times d, so take it 45 mm. Okay, clear? Then empirical relation for outside diameter of the eye and the fork. So this is the eye inside diameter. So what is the inside diameter of the eye and the fork? d1, which is equal to p. And what is outside diameter? d2. I am repeating this again and again because further analysis you will require this. So how will you calculate this? d2 is equal to empirical relation twice of d, twice of d. Is it clear? So d3 is equal to 1.5 times of d1 d, and empirical relation for d 2d, d2 is equal to 2d. And so what is d? D we have already calculated as a 30 mm. Is it clear? So in this way we have to calculate, sorry, this is not D, basically by mistake it's D1. Okay, it's D1, don't get confused. D1, what is D1? Diameter of the pin. So this D3 is taken as 50% more than pin diameter, so D3 is equal to 1.5 D1, and D2, that is the outer diameter of the eye and the fork, is taken as 2 of D1. Okay, D is the diameter of rod, D is the diameter of rod, which is 22 mm. Okay, and D1 we have calculated. So up till now you might have understand that D1 and D, diameter of the rod and diameter of the pin, we have calculated from the stress analysis, but D2 we have calculated on the basis of, the rest we have calculated by using empirical relations. Okay, so now let's move on to the next part, that is the stresses in the iron. Now we have already done the analysis of rod and done the analysis of pin. So now remaining two parts, one is the eye end and one is the fork end. Okay, so basically now you can see that this is the eye end. In the eye end you can see this is a hollow portion. Okay, this is a hollow portion. So obviously it is a hollow portion, means what? There is a stress concentration over there, there are chances of failure. So when the force P, that is the tensile force P, is acting equal and opposite, okay, you can see that this eye may break at this section x. Okay, so you can see here, I have shown here. Okay, now this middle portion is a hollow portion, so this area will be only the area resisting the tensile pair. Tensile means what? You are applying pull on both the ends of the eye, so eye will break. So obviously where it will break? It will break where there is a hollow portion. It will break because there we have, there is the material, it is a weaker section, you can call it as a weaker section. So x is nothing but a weaker section. Okay, so basically you can remember like this also, when the plane of the failure is perpendicular to the direction of the force. So let us say this is the direction of the force, and let us say this is the plane of the failure in which the tensile failure is happening. So if this is perpendicular, then the failure is either tensile or failure is either compressive. Is it clear? Okay, so now basically what is the first step? To calculate tensile failure, sigma t is equal to P upon area. P is given, sigma t we have already calculated. The important part is nothing but A, and this A is nothing but the area resisting the tension. Now what is area resisting the tension? Obviously this area, right? So how will you calculate this area? Again very simple, let me take a figure over here. Okay, so let us say this is the outer diameter of eye. Now talk about the eye, right? This is d2. What is the inner diameter? d1. And again come here, what is this thickness of the eye? T, right? So guys, what will the area resisting the tension will be? d2 minus d1 into T. Is it okay? Very simple. Yes, so here in this way, so that is why I have shown this three-dimensional figure. So this area Okay, this area will be nothing but this d2 minus this d1 into t. And once you are able to calculate the area, you can calculate from here also. See, this is d2, this is d1, d2 minus d1 into t. Why t? Because we are considering a I, and thickness of I end is a t, and thickness of forkend is a t1. Okay, so area this thing will be t into d2 minus d1. T is 30, 60 d2 d1 30. Calculate. So 900 mm square. So now no need to use this sigma t. Now we'll use a different case. Okay, sigma t is equal to p upon area. P we know, area we have calculated. What is the answer? Answer is 55. So now what you have to do, what is your allowable stress? 155. So if now this is nothing but the tensile stress, sigma t is what? This sigma t what you have calculated is not a design stress, it is the actual stress. It is the actual stress, means what? It is the actual stress which is acting here, actual tensile strength. And if guys try to, if this actual tensile strain 55.55 is less than your allowable, what is your allowable means what? Allowable means what? Permitted. So if this actual stress which is created in the I end is less than allowable stress, you can say that sigma t which is actual is less than 155. You can say that the tensile strength is within the safe limit and design for tensile failure is safe. Means what? This particular I, one second, this particular I will not fail due to the tensile, because maximum actual stress which is created is nothing but a 55. But what is allowable? What this material can sustain? Material along with the dimensions, that is a geometry, can sustain 155. I hope it is clear to all of you. Now shear failure. Now guys, try to understand that this is a I end, right? So if you consider this I end, you look at this figure and look at this figure. So this is a P force P which is acting. Now basically you first of all understand that in initial case this plane was perpendicular to the force. Okay, now when the plane of failure is parallel to the direction of force, means what to say, now you consider this plane. Okay, so now we are talking about this plane. Now this plane is parallel to this P, right? So when this plane, the plane of failure, so I am talking about this plane. Now you can see this plane, parallel plane. Okay, so if you are looking in this parallel plane, so in parallel plane this P, okay, the direction of force is parallel to the plane of failure. The failure will be the shear failure. So obviously this I will also fail for the shear in this parallel plane. Okay, so how we can see here? So this force P, okay, obviously the force is tensile force only, right? But the plane of failure is parallel to this force now. Okay, the plane of failure is parallel to this force. Okay, so in this plane what will happen, this portion you can see, this small portion which is been removed from this removed means what? This small portion is sheared. Okay, so obviously you have to imagine this now, this small portion which is sheared because of this force P in the plane of failure which is parallel to the direction of force, we call it as a shear failure. Okay, so in tensile failure, don't get confused, in tensile failure in this way it failed, in tensile failure it failed in this manner. In shear failure, that is why I have shown this diagram, this portion is sheared, removed. Okay, now we have to obviously first of all find out the area resisting the shear. So this is nothing but the area resisting the shear. So how many areas are there which are resisting the shear? How many areas are there which is, this is the one, and obviously from this side there will be two, so there will be the two areas. Why two areas? Because this area is also filled, this area is also filled. Okay, so this area and this area here, I will make it clear once again. This area, first area, and draw like this line here, this is the second area. So there are the two areas which are resisting the shear failure. Now how will you calculate, now we know that tau is equal to P upon area. What is tau? Tau is the allowable shear stress 71, 75. So whatever the stresses, shear stress created in this portion, it should be less than this allowable stress. So for that, how will you calculate the area? So see, this total distance is d2, this distance is d1. Okay, so obviously d2 minus d1 will give you this plus this. Okay, but I only want this, means what, half of this. This is 1, this is 2, so this 1 plus this 2 is nothing but a d2 minus 2. So if I just want only half, so I will take d2 minus d1 by 2, because I just want this much, na? This is including this plus this, forget about this hollow portion. I know this is slightly complicated. This plus this, forget about this hollow portion, is nothing but a d2 minus d1. So I just want this half portion, so d2 upon d1. And what is the height? Height means what? Thickness t. So guys, what will be my area? Very simple. Area will be d2 minus d1 divided by 2 into t, multiply by 2. Why 2? Because there are two areas resisting the shear failure. Okay, so you can see here, it is also shown in this diagram. So I hope it is clear to all of you. Okay, so tau is equal to P upon area. P is 52 into 10 is to 3. What is divided by, what is area? 2y, double shear, two areas, d2 minus d1 into t. So from this, after calculation, yes, so I am happy. The actual shear stress, actual shear stress will be 55.55, which is less than the allowable shear stress. So you can say that the design is safe for the shear failure. Is it okay? Is it okay? Okay. So now let's move on to the another problem, the crushing failure. Now again I am requesting you to watch the videos. The crushing failure. Crushing failure means what? First of all, let us understand. The single eye is also subjected to the crushing. You take an example. Let us say you take an example of a metal piece. This is a metal piece. Okay, a hollow metal piece. Let me draw it more clear. Let us take an example of a hollow metal piece, and this is obviously a ductile material. Any metal, take a brittle material. What is brittle material? Chalk. Now the chalk is having a diameter d, this diameter is also d. Now the diameter d chalk you insert inside this hollow metal material. So what will happen? That chalk will get crushed into the fine particles. Means what? Let us say this is a chalk. So on this surface area of the chalk, the crushing stress, that is a localized compressive stress, was induced. You can see here C, sigma C. So that is why what will happen, the chalk will get crushed. But in the our metal, there is a pin is not made up of a chalk or a brittle material, chalk material or brittle material. Obviously we have properly selected the dimensions and material. Okay, so obviously this pin will not get completely crushed, but you have to also design it for a safer side. So you have to also calculate what are the crushing stresses acting on the pin. Okay, when the pin is inserted inside the eye as well as the fork. Now you can know that this portion of the pin T1 and T1 is inserted in the fork, and T is inserted inside the eye. So there will be the crushing stress created in this manner. See, sigma C is nothing but a crushing stress created at this T portion, is the T portion, but this T is due to the eye and T1 is due to the fork. We'll understand about the T1 later on, because we are now talking about the eye only. Okay, now so the crushing stress is nothing but a localized compressive stress between the pin and the inner face of the single eye, right? Now basically in crushing failure the area is curved. See, this area is curved, na? You can see this area is curved because it's a pin, circular cross section. Okay, but we are considering a projected area. See, I have projected this. Now what is this projected area? This, it's nothing but a rectangular area, so we are considering it as a rectangular area only, right? Even if the projected area is curved, we are considering a projected area which is in a cylindrical form, right? So what will be the area? So this area I will draw here, this area, a projected area having, let us say this will be T, na? T means what? The thickness, the portion of the pin which is inside the eye, and let us say this height is nothing but the diameter of the pin. So in this case the diameter of the pin is obviously D1. Okay, so this area which is resisting the crushing failure will be a rectangular area T into D1. I hope you have understand this. Okay, so we know, basically I will explain you. Okay, now here it will be more clear. See, what is this total height? This total height is nothing but a T. What is this total? Let us say this is T, and what is this total length? B. Means what? It is a D1, diameter of the pin. Now what I mean to say is that inside this particular, you can say eye, the pin is inserted. So what will be the projected area on which the crushing stress is acting, or the resisting area, right? So obviously we are considering as a projected area. Projected area is nothing but a rectangle, right? So what is a rectangular area? This T multiplied by D1. So guys, the crushing failure of single eye resisting area is nothing but a projected area which is equal to T into D1. Is it clear? And crushing area is nothing but the crushing stress is nothing but a localized compressive state. So what is the formula? Sigma C, that is the localized compressive state, is equal to P upon T into D1, which is nothing but the P upon area. I hope it is clear to all of you. So P is 50 into 10, T we know 30, D1 is nothing but diameter of P. So what is this? 55 upon 55. But what is the localized allowable compressive stress? It is nothing but a 32. So 50.155 is less than 32 means what? Your pin will not get crushed. So your pin, when you will insert inside this eye, about the fork we will understand later on, but this T portion of the pin which is inside the eye will not get crushed. Clear? Okay, so this is called now checking the stresses inside the forkend. Now very important, no need to do the all the further analysis, because the forkend is also subjected to the same failures as that of eye end. The only difference is it has two eye and its thickness is T1, so we get the same equations except multiplied by 2. So equation for tensile, shear and crushing failures will be same, just multiply by 2, and instead of T1, I will go back just for a purpose. Just for a purpose I will go back, because it will be easy for you what I am trying to understand. See, so this thickness is T1, outer diameter is D2, inner diameter is D1. So here inner diameter is D1, outer diameter is D2. Only the difference is what? Here the thickness is T1. Okay, so obviously this I, we have done the stress analysis for tensile, shear and the crushing. Similarly, same equations will be applied for this fork, but these forks are 2, 1 and 2. So just multiply by 2. है ना? Okay, so no need to do all this analysis once again, directly go for the this one. So first tensile failure. So what was the formula for tensile failure? Tensile failure of the eye. Tensile failure of the eye, what was the formula? Sigma T is equal to P upon area. And what was area? Area was T into D2 minus E1. Okay, so I have used the same formula, just instead of T1 T I have used T1 and just multiply by 2. Is it okay? Clear? Instead of T1, instead of T, use T1 because the thickness of the fork is T1 and thickness of the eye was T, and multiply by 2 because we have two forks. Okay, is it clear? So 60 is equal to 46.29. This is the actual tensile stress inside the fork. So fork will fail in the same manner. The tensile failure of the fork will be same as the tensile failure of the eye, so which is less than 155. So I can say that design is safe for the tensile failure. Then for shear failure, again P tau is equal to P upon area. What was the area for that? What was the area for that? The area for that was P upon T into D2 minus D1, right? P into D2 minus D1 divided by 2. Is it clear? So So same formula again we'll use here, same formula we'll again use here, and so finally you are getting a formula. So just here multiply by 2, and instead of t you take it as a t1, so you are getting tau is equal to 46.29, which is less than 77.50 Newton per mm square. So you can say that the shear stress is within the limit. And similarly for the crushing failure, formula will be same. There it was t1 into t, here it is t1 d1 multiplied by just 2. And again, so guys, you can understand one point here, I will explain you that. 46.29, so sigma c is less than 232. So we have taken sigma c is equal to 1.5 times of sigma t. So you would have considered it as a 1.2 of sigma t. That was also okay, because these crushing stresses are very less as compared to the 232. Okay, but that doesn't matter much. So this is how, I hope you have understand this. Okay, and the x is usually taken as x. What is x? I will explain you. Okay, so just let me go for backward. Okay, so what is the final step? So this is the x, yeah, this distance, okay, x. Okay, so what is the final step? The final step is that you have to draw this. Already you might have drawn this diagram. Draw this diagram and show all these notations here. What is t2, what is t1, what is t. Now whatever the design you have done, so you have to do the solid modeling of this design using Fusion 360. Okay, after doing this all the calculation. So I hope you have understand this, the design of knuckle joint. So you can watch this video repeatedly along with the basic videos, you will understand. Okay, so notes has been mailed to your Google Classroom. Thank you so much. So in the next lecture maybe we'll understand the design of quarter joints.